Okay, so let's move on to kiln firing and things that terms that relate to actually firing of a kiln. And one of them, again, this may be familiar to everybody, is just the term reduction. And what this is something that occurs when you're burning something, basically. So you don't get reduction in an electric kiln. What it refers to is it's the atmosphere or the mixture of gases that you have in the kiln, and you have an excess amount of fuel or unburned fuel. So I'm burning something, and I haven't provided enough air to completely burn all the fuel. And so then the kiln goes into what's called has a reduction atmosphere. And when you're getting a reduction atmosphere, and the reason why you do it is we do it for color. That's the only reason we fire in reduction. That's the only reason we fire, other than maybe we don't have an electric kiln. But the only reason because a reduction atmosphere causes actually certain chemical reactions with certain elements. Iron is one of the major ones, but also copper. And it changes the color of the compounds that they form. So we fire in reduction to get certain colors out of a clay body or certain colors out of a glaze. And the main chemical agent in the atmosphere that's doing the reduction is carbon monoxide. Not soot, carbon monoxide. And you know how you hear warnings about like your furnace or your heater, beware of carbon monoxide? Because if you're not venting your furnace or your kiln or your heater, whatever it is, completely, you will produce some carbon monoxide. Or if your oil furnace or your burner isn't operating efficiently and it's not producing enough air, instead of producing just carbon dioxide and water in the exhaust, you'll produce carbon monoxide. In this case, we want to do it. We want to create carbon monoxide in the kiln because this reacts with some of the other elements in the kiln, iron and copper and other things, and changes the colors that I get. Okay? So reduction is not having adequate air to burn all the fuel. It's like your car running, you hear about a car running rich, which means your fuel system and your air is out of adjustment, especially with carburetors, not so much anymore. But where you talk about a car running rich, where you have, and maybe it even backfires to something because you have too much fuel and not enough air, you're doing the same thing. And so a good example, for instance, so like iron, if you have iron in a clay body or iron in a glaze, in oxidation, typically you're going to get colors like yellows and browns. But in reduction, you can get green. Or copper, typically in oxidation, depending on the glaze, you're going to get greens or blue greens or something like that. In reduction, you can get red, because you're changing the chemical form of the copper on the iron as a result of reacting with the carbon monoxide. Okay, so let's go into another term now. This is another one of the headline terms, quartz inversions. This is probably the most complicated. Quartz inversion. Everybody heard that term or something? Or silica inversions. Sometimes you'll hear silica inversions, which chemically is this. SiO2 or silicon dioxide. It's a really common material. This chemical actually exists in several different forms depending on where the atoms are arranged. And those forms have different names. And one of the forms is quartz. And there are just two kinds of atoms, silicon and oxygen. But depending on the way they're arranged or the details of the arrangement, you end up with structures that are slightly different. And so they have slightly different properties, so they give them different names. Okay? So quartz is one type of structure, and that's the stuff I showed you earlier. This is quartz. So this is chemically, it's silica, but the name we give it is, this is a mineral name. This is really common mineral, is quartz. Now there's another form of it, slightly different, same chemical, it's called cristobalite. Cristobalite, that's still silica, but it's another slightly different arrangement of the atoms, has slightly different properties, so we give it a different name. To make it even further complicated, each of these has two slightly different forms. So there's alpha quartz and beta quartz, and then there's alpha and beta cristobalite. It's all this stuff. I have a certain type of structure and two slightly different variations here, and then I've got a significantly different structure, still this stuff, and two slightly different variations. Okay. Now, so now if we go back to, let's talk about a clay. All this stuff, what we really count, this is reference to clay bodies. That's where this stuff is, where we're going to get into. What happens is all clay bodies basically contain some quartz. Quartz is a natural mineral, and matter of fact, most of the clay that you buy, if you just buy plain clay like EPK or kaolin clay, that also contains a lot of quartz. It's just there, and it's there because of the way the clay formed. Clay forms from pre-existing rocks, and those pre-existing rocks almost always contain quartz. Well, when the rock is modified and changes into clay, the quartz just comes along with it. So there's quartz everywhere, basically. If you look at it, you're all familiar with the term MSDS, Material Safety Data Sheet. If you look at a data sheet for ball clay, it says that the ball clay can contain up to 30% quartz. So what you think is pure ball clay isn't even pure clay. It may have up to a third of quartz in it. Totally different material, totally different mineral, okay? So quartz is everywhere. So when I have a clay body and let's say I've got a couple of clays in it, and maybe I've got a flux like nepheline cyanide, some other stuff, I've also got a lot of quartz, okay? So now what happens, so what do these things do that we're concerned about? And we'll call this size. How about that, okay? So I heat it up, gets to a certain, it gets bigger and I continue to heat it. And then as I cool it back down, when it gets to that temperature, it shrinks back down again. Cristobalite does the same thing, but at a different temperature. When I get to a certain temperature, it jumps up and shrinks back down. So what this means is if I've got a clay body that has quartz in it, as I'm heating up that clay body, when I get to a certain temperature, roughly 1,000 degrees, really roughly, all of a sudden all those little clay particles are going to want to expand. And then I keep heating it up, and then as I'm cooling the clay body back down, the firing is done. When I get to a certain temperature, same one, about 1,000, all those little quartz particles, if they're still there, are going to want to shrink all of a sudden. Well, if I get too much of that all of a sudden shrinkage during cooling, the pots will crack. That's called dunting. That's what dunting is. Dunting is where the pot basically tears itself apart because cooling down, there's so many little particles in there that are shrinking all at once. The pot literally can't stand it, and it tears itself apart and cracks. Quartz generally is not that much of a problem in terms of contributing to it, but cristobalite is, because cristobalite expands and contracts more than the quartz does. Now, the weird thing about this is there is no cristobalite in your clay to start. You make it when you heat up the clay. When you heat up the clay, the quartz changes into cristobalite when you get up to high temperature.
But not all.
Not all of it. It all might be, or none of it might be. So I start off with quartz, and it expands on the way up. Then I take it up to high temperature. Some of it might change over into cristobalite, and now I'm cooling back down. So now I've got quartz and cristobalite, and both of them shrink when they reach a certain temperature. And if the shrinkage is too much, it tears the pot apart. So together, all of these changes are called the silica inversions. This change of one structure to another is called an inversion. So collectively, these changes, expanding when you heat it up and cooling, are called the silica inversions, because these are all forms of silica. But you may hear talk about, then people will say, well, the quartz inversion or the cristobalite inversion. Well, now they're talking about that particular material. But collectively, they're all forms of silica, so they're all the silica inversions. Now, there are a couple of things that surround this. There's kind of what I consider to be kind of a myth that you can't heat pottery up too quickly because the quartz will expand and crack the pots. I think that's a lot of baloney. Because when you're heating up a pot, a bisqueware, and these little quartz particles want to expand, as you know, the bisqueware is very porous. And so each little particle has room to expand. It can just go crunch and expand into all the space around it. The problem occurs when you're cooling down is the fact that now the piece is solid, and if pieces want to contract, there's nowhere, the things can't move. They're essentially locked in place. And to me, that's where the problem happens. And the main cause of dunting is really cristobalite. There may be some quartz left, and that may contribute to it, but cristobalite, because it shrinks more, it contracts more than the quartz, and if you make a lot of it, then the effect can be significant. That's the main thing that contributes to dunting. So the real problem comes in, but it's not so much even the cooling is making it. This is why, like with long wood firings and these long firings, you make a lot of cristobalite because you're sitting there up at high temperature, just cooking the clay. And when you're getting to the high temperatures, the quartz wants to change into cristobalite. It wants to change. It wants to become cristobalite. So the longer the firing is, the hotter the firing is, the more cristobalite you're making. And it also depends on what's in the clay body. If I have a lot of little tiny fine quartz particles, they want to become cristobalite more easily than big quartz particles. So it can come down to something as simple as one ball clay in my clay body versus a different ball clay. If the one ball clay has a lot of fine quartz, that might cause me to form more cristobalite and cause dunting, and a different ball clay might not do it.
So when you say the change, are you talking about the change from quartz to cristobalite or the change in the contraction of the whole?
Quartz to cristobalite.
Okay.
Because we're making cristobalite. The clay bodies don't start out with cristobalite in them. They only start out with quartz. And then I take it up to high temperature. Some or all of that quartz now changes into cristobalite. And then I cool it back down. And when I cool it back down, the quartz wants to shrink at about 1,000 degrees. Really, these are really round numbers, but I think it's easier to remember. Quartz wants to change at about 1,000. Cristobalite wants to change at about wants to shrink at about 500. So the thing is to work backwards. If you're getting a lot of dunting, is to say, okay, well, what's my problem? And the two things to think about was, am I firing for a long period of time, in which case that can certainly contribute to it, or is it my clay body? Do I need to change my clay body? And if you're using a commercial body, you have no idea what's in it. But this is why some people like to make their own clay bodies. Because if I know what's in my clay body, I know the ball clay and I know the stoneware or the fire clay or whatever in it, then I can say, okay, I'm going to do a little research. I'm going to look into my raw materials and see, is there a possibility that maybe one of them is causing the problem? And I'll change it. I'll make up a test batch. I'll change that raw material and see if I still get the dunting. Okay? But anyway, so the whole point of this, all this complicated, besides I just wanted you to know what the term, or hear the term, it's the silicon versions, is really, it comes down to dunting. Is that if you're getting this catastrophic cracking, is to what's causing it? Well, this is probably what's causing it, and it's either due probably the fact that either you've got your clay, but there's something in your clay body that's making a lot of cristobalite, and or you're firing for a long period of time and making a lot of cristobalite. And in this case, the one that I was telling you about, the fellow that made the tankards, this was a wide range clay body. It was a Campbell's clay body, and so we don't know specifically what was in it. But he changed the clay body and nothing happened, no problem at all. So it was definitely something in the clay body. Too much fine silica, we don't know because we don't know what was in the body. That's the problem with, if you have a problem with a commercial clay body, you don't know what's in it. So that is one argument in favor of making your own, is that you know what's in it and you can attack a problem like that. Okay? Okay, heat work. Again, you've probably all heard the term, but I just wanted to include it in today's discussion. Is everybody familiar with this or heard about it? Okay, so I don't need to talk about it a whole lot then? Or the whole point is that when we're firing pottery, we should never be firing by temperature. We should always be firing by heat work. Firing pottery or firing clay is analogous to doing a pot roast or a roast in your oven. If you're doing a roast in your oven for 3 hours at 350, you wouldn't say, well, I'll do it for 1,000 for 5 minutes. Because it won't work, right? Because things have to happen in the roast in order for it to get done. Well, the same thing is true with the clay and the glazes. There's a whole sequence of chemical reactions and changes that have to happen in the clay and in the glaze. So we need time as well as heat. So we really talk about heat work, and this is why we talk about cones, because cones respond to heat work. Because cones, in fact, are little clay bodies. And so the way a cone responds to heat and time is exactly the same way our pots respond. They soak it up, those changes are going on inside, and they respond to it. So temperature is just an instantaneous tell us of something going on, but it doesn't tell us how the pot is actually responding. So that's what cones are doing. Cones are measuring or reflecting heat work. And that's the way we should fire, because you need time for all those things to happen. There's a whole sequence of chemical changes and physical changes that happen in a glaze and in a clay body as you heat up in temperature. And they have to happen in order for the clay body to be mature or the glaze to melt properly and perform the way you want it to melt. So we need the effect of time. So, I mean, literally, you should always be firing by heat work. Don't trust your electronic controller, because they're not that accurate. You should always, this is my own personal opinion, but you should always be firing with cones. I put cones in my bisque firings, because I want to make sure that if the bisque is different, you know how that affects the absorption of the glaze? So I want to make sure that my bisques are always fairly consistent, so that my glaze absorption will always be fairly consistent. Okay? Okay? Okay, along with cones now, there's another sort of weird effect that doesn't have a specific name, but I'll describe it and see whether you've heard about it or not, is that if I put a certain cone in a kiln, let's say I put in a number 6, and I fire in cone 6 bends, if I fire at a different heating rate until cone 6 bends, I end up at different temperatures. So if I'm going to do a cone 6 firing and I fire slowly up to cone 6, I'll reach a certain temperature. If I repeat that firing and I go very quickly up to cone 6, I end up at a higher temperature. The actual temperature is higher, even though the cone 6 is doing exactly the same thing. And the reason, and this shows up in the fact that I run into this a lot with teachers who are under pressure in schools or in institutions where they got to crank a lot of pots through, and so they almost always do the fastest glaze firing they can do. And I've had people say, well, then, I did a perfect firing. I put cones in. The cone is just where. By the way, when a cone bends, you do it until just the tip touches. That's down. When it's lying like a limp amoeba or blob on the floor, that's overfired. So you fire it until the tip basically touches the same level as the base. That's done. Anything past that is overfired. So they say, well, I did it perfectly. My cones look like this, and all my glazes ran. And so the first thing I'll ask them is, well, how quickly did you fire? And they say, oh, it was the fast firing. Well, that's the answer. Because with the fast firing, they ended up at a higher temperature. It could be 20, 30 or more degrees hotter. That's enough for some glazes to make a difference between running and not running, especially at cone 6 or especially at earthenware. What Steve just said, I'm firing to the same cone, right? The same cone is going down. But if I'm firing slowly and the cone goes down, I've got a certain area, a certain amount of time. If I fire quickly, I've got less time. But in order to have the same combination of time and temperature, the same area, I've got to have more heat, which means more temperature. So this is and the thing is, this is especially true for earthenware and for cone 6 glazes. There's a natural progression. Most earthenware glazes are very temperature sensitive. Cone 6, not quite so much. Cone 10, the least. So you probably run into this, but like there are some cone 6 glazes, if you don't hit it exactly on the cone, it's under or over fired. Okay? So it's 20, 30, 40 degrees for some cone 6 glazes is enough to make a difference between running and being really nicely done. Just a couple more terms, we're almost done here. I don't know whether you've ever heard this term, eutectic. This is why glazes melt, basically, because what this basically says is if I have two different materials, this is temperature, and this is material A and this is material B, and this one melts at this temperature and this one melts at this temperature. If I make a one-to-one mixture, you might say, well, it's going to melt there. Not necessarily. It actually, in fact, it might melt there. And the idea is, what a eutectic is, when you combine two materials, not any materials, the combination of the two in a certain amount melts at a lot lower temperature than either one of them does by itself. And what you say is that the two materials have formed a eutectic. That's the way the term is used. Or this is the eutectic that forms between those two materials. And this is what fluxes do. This is why when you add a flux, the silica wouldn't melt by itself. But these other things we add as fluxes form eutectics with the silica, and together they melt at a temperature that we can accommodate or use in our kilns. So this is kind of the basis. This is when a kid, if somebody ever asks you and says, well, how do fluxes work? All you have to do is say one word, eutectic. I'm kidding, but that's the answer. Especially if you want to impress them, you just say, well, it's just a simple binary eutectic. But that's the principle. Is that just this? You've heard this term a lot, but that's what it means. It just means that the two things together melt at a lot. So if I take like soda ash and I mix it with quartz, they're gonna melt at a lot lower temperature than either one of them would by themselves. And so that's great, because now it brings it into a range where we can reach it with our kilns. Whereas we couldn't use glazes if the silica didn't melt at a lower temperature. We couldn't reach it with our kilns. We'd have to have fancier kilns. This is the last term I just wanted to bring up. Coefficient of thermal expansion, which is abbreviated as CTE. Usually among potters, glass workers tend to abbreviate it as COE, coefficient of expansion, but it's the same thing. And what it really refers to is the fact that every single solid substance that we have, when you think about it, if I heat it up, it just naturally expands, and when I cool it down, it naturally contracts. It usually comes right back to where it started, right? I mean, you take advantage of this when you have a jar of spaghetti sauce and you can't get the lid off. You hold it under hot water and the lid gets looser. That's because the coefficient of thermal expansion, the amount the metal lid expands when you heat it up, is more than the glass, so the lid gets loose. So you're taking advantage of a difference in the coefficient of thermal expansion of the steel lid and the glass jar when you're loosening that spaghetti jar lid. So all this, so every material around us, everything in here has its own number. It's a number that basically says how much it expands when you heat it up a certain amount. So if I heat up a piece of steel, that piece of steel will not expand, for instance, as much as when I heat up a piece of aluminum. Or a piece of oak will not expand as much as when I heat up a piece of eucalyptus. Everything, or different kinds of plastic, they all have different characteristics. Well, why do we care about this? Because this comes into play when glazes are cooling down, primarily. And this comes into play when we have the two sort of glaze problems of crazing, and we also have the problem of shivering. Think about this. Think about, I've got a glazed pot, and I heat it up to high temperature, and I'm done. I consider my firing over with. I turn off the kiln, and now the first thing that happens, major thing, is the glaze solidifies, right? The glaze is liquid at high temperature, so now it turns to solid. The glaze freezes. So now I've got solid glass sitting on solid ceramic, and I'm cooling it down, both down together. Well, each one of those materials, the glaze and the clay body itself, are going to contract at their own rate as they cool. Because they each have a different coefficient of thermal expansion, a different number that characterizes how much they shrink when they cool, right? So crazing is because of the fact that the coefficient, the coefficient of thermal expansion of the glass is higher than the clay. That means that the glaze wants to shrink more when it cools than the clay does, and if it happens in excess, then you get crazing, because the glaze wants to shrink more and contract when it cools, and if it's a lot more, it'll crack. That gives you crazing. If the other thing happens, if the clay body, I've got this hot clay and this hot frozen glass, if the clay body wants to shrink a lot more as it's cooling, a lot more, I get shivering, because the clay body contracts a lot, so much so that the glaze can't stay stuck to it, and it pops the glaze off. So we care about this. This term comes into play. This is one of the main reasons where it comes into play with these two defects. So that when to get the proper glaze fit, and you hear about the term glaze fit a lot, you want the coefficients of thermal expansion of the clay and the glaze can't be really wildly different, or you'll end up into this situation. So the ideal situation for glaze is you want the coefficient of thermal expansion of the clay to be slightly higher than the glaze. You want the clay to be squeezing the glaze a little bit when it cools, and that gives you that really strengthens the glaze a lot. So that's the ideal, and this is what they do in industry and in ceramic companies where they can engineer these things more precisely. They'll formulate a glaze to contract slightly less than the clay. So the clay is squeezing it, and that's the strongest possible situation for the glaze, to be squeezed slightly by the clay.
So if you are having issues, it's just a matter of changing materials to find the right fit.
Yeah, I mean, and for instance, I mean, it's known, for example, like this is where our old friend sodium again. Sodium and different elements, for instance, in a glaze, and it's easier to adjust the glaze than it is the clay body, especially because you're using commercial. But our old friend sodium not only does it cause deflocculation in the glaze in the bucket, but also sodium has a really high coefficient of thermal expansion. So if I have a lot of sodium in a glaze, I can guarantee that glaze is going to craze. Because a lot of sodium, it gives it a high coefficient of expansion, and when that glaze cools, it shrinks like crazy, and it's going to craze. Which is why, for instance, carbon trap glazes, carbon trap chinos that have soda ash, craze, because they have a lot of sodium in them. Okay, that's about all I had. Does anybody have any other questions? Well, I guess basically what I was hoping to accomplish with the terminology, even though a lot of them seem unrelated, I was hoping to at least show that there is that there is some application to us, or really what the application is, so that it's not so much the terminology that's important to me as the understanding of what they relate to, and why do we care about it? What's important about it, rather than so much just superficially what the name is. Because you hear a lot of people sort of throwing these terms around, and half the time they don't know what they mean anyway. But anybody have any questions or comments or anything? Okay, well, thank you very much. The topic next month is going to be tips for successful glazing.